All right, what's going on, everybody? This is Mr. Diamond, and this is going to be a little bit different than the normal videos that I do for notes. I've been thinking after my video that I recorded and put out yesterday, if this is the first year that you're taking this class, and I realized that I wanted to do something else because I feel like I might have answered some of the questions, but I also am assuming I've probably still got a couple of questions left that I need to answer. And I was trying to come up with what's the best possible way to explain that. And the best thing that I could come up with was I'm going to kind of just talk through. I don't have any notes or anything. I don't have any other explanation pieces. I'm just going to talk through all of the types of things and the types of forces that are going to show up in this chapter. So we'll start with Newton's laws. And again, I don't have a direction for this. This is going to be me basically just, I guess it might be a little bit rambly here. So first is object in motion tends to stay in motion. The real idea or the real importance of that piece of Newton's law or that idea is mostly so that way it kind of explains the foundation of all of the other laws and all the other things that we're going to be talking about. It doesn't actually directly tie into any real equation that we're going to be working on for this chapter. And the only other key idea is that if we go to like the actual like more specified or like in detail definition, it says tends to stay in motion parentheses unless a net force acts upon it. So this is just kind of setting us up for most of what we're talking about for the rest of them. This is also referred to as the law of inertia. Now, second law is where we actually can start getting some mass involved in it, and or math involved. There's a little bit of a slip there, but mass is what we're going to be caring about. So second law says a net force, which remember it says we need a net force up here to prevent an object from staying in motion, will change the velocity of an object. And it could speed it up, it could slow it down, but changing of velocity, remember, a change of velocity over a change in time or over a certain amount of time is acceleration. So this second law is how we're going to relate it. Now, this was also called law of inertia. Mass is also the thing that affects how difficult it is to get something moving. So that means we have to relate the net force or the sum of the forces to mass and acceleration. And that's where F equals ma comes from. And this is also the reason both of these together is why if something is at rest or at a constant velocity, although we haven't really done anything with constant velocity, we say that means acceleration is 0, so sum of the forces is equal to mass times 0, which is equal to 0. So we know all of our forces that are involved will have to cancel each other out if that is the case. Now, the third law is the one that is the least direct in what we've been talking about or what we've been caring about. But is still really important conceptually, and that is we're going to use the bad language for it, which is every action has an equal and opposite reaction. Again, this is not the most accurate way of representing this idea. If I pull up my notes that I think I have close by, like the PowerPoint that I have close by, I think I go into detail that it's a force acting upon one object will cause the second object to exert an equal force in the opposite direction on the first. Really what this means is this law right here, Newton's third law, is it going to explain things like tension and the normal force specifically. So let's go through and let's think of every other type of force. Now we've got our background, our ideas of all of our laws. Let's break down all of the types of forces at play. So the one that everybody seemed to be pretty confident is the force of gravity. On Earth, the force of gravity is always equal to mg. It's always directed downwards every single time. Now, normally when something's falling, if it's in the sky, it will continue accelerating down. So when something is in the air, gravity is the only force that's pulling upon it. However, if something is not on the ground or in the air, if it's actually just resting upon something, we need to have something that is keeping it at rest, because if it's just sitting on the table, it still has gravity acting upon it. Like this pen has gravity acting upon it, but it's not accelerating. It's not changing its speed, because objects tend to stay in motion unless a net force acts upon it. So that means something must be preventing it to be a net force, and we call that force the normal force. So the normal force, and that normal force is going to be the force that supports or counters gravity when an object is at rest. It's technically not just when gravity. It can also, like when you push against a wall and the wall pushes back on you, that's also an example of the normal force. So normally when you're trying to calculate the normal force, pun slightly intended, normally what you're going to do, if it's flat, they're usually going to be equal to each other. We've got Fg down here, Fn. If there's no pull or push in the y direction, then force of gravity is equal to the normal force. Pushing down on the box or lifting up on the box can change the normal force. Gravity is always going to stay constant, however. Now, normal force also connects to a different type of force that we have, which is the force of friction. So this is the frictional force. And specifically, normal force always is directed perpendicular to the surface. So in a box that's resting on the ground, normal force goes up. If it's on a slope, though, normal force is at an angle, while gravity is still going to point downwards. Okay, normal force is related to frictional force, because frictional force is a measure of how much the atoms and the surfaces of two materials are going to resist motion and make it harder to move. The rougher something is, that's more points of contact, that's more difficulty that you're going to have to move something. The less friction, the smoother something is, that's the less individual surfaces that are in contact you have to account for, and that's going to be a lower coefficient of friction. There's two categories of this. There's, well, we'll go ahead and call it kinetic. We'll call it that because it's its name. And static. Static is when it's stationary. Kinetic is when it is moving. Both of these have their own coefficients, or mu k and mu s. And the whole point of friction is that it will build to resist if it's static friction, and it will have a constant rate of resistance if it's kinetic. For static friction, what it means by that is both of these frictions will increase or change based on the force that's being applied to it, up to a point for static friction, though. For static friction, again, what you normally do is if you calculate the maximum static friction, you would take and you go, well, let me take my coefficient and let's figure out what the normal force is. And that is the maximum number that it can get. So static friction will increase to this number. So if it's 100, the maximum static friction is 100. If it's 400, the maximum static friction is 400, whatever it is. And then if it increases to that number, then anything more, it moves. And you have to now use mu k. And again, just because you count this, this is the maximum static friction. If you push sideways with a force of 5 newtons, static friction, as long as 5 is not its limit, 5 newtons is what will be pushed back on you to keep it still. Because again, the whole point is you want it to have a no net force. If it is still, if it is at rest or at a constant velocity, the sum of the forces has to be 0 because there's no acceleration. So when you push on an object, if you don't overcome static friction, like I'm not doing right now, whatever force I'm pushing is how much force static friction is going to give back to me. And it's going to go up and up and up and up. And I explained this in the last video, but it's kind of like a graph. And I'm going to explain that idea a little bit better here, I hope. So I've got force, and then I've got static friction. So what they're going to do is they're going to increase and increase and increase until you hit a certain point. And this point is going to be F static max. And once you go beyond that point, your force can increase, but your static friction is no longer going to do. Past this point, the object is going to move, and we'll actually switch to, and it will probably be lower down here because this kinetic friction is going to have a lower coefficient. It'll actually jump down here, and you'll have force of kinetic friction that will increase down here. And again, it will drop because, like we've looked at before, all of the coefficients of static friction are always higher than the coefficient of kinetic friction. So your force that you're adding and how kinetic friction responds to it will have dropped. You'll have less friction at play with that force that you've added. This graph, I guess, is not actually, I guess it would actually probably be more like over here or something like that. Like it would be the same force, but it would be less friction at play. So I guess it'd be more that direction. But the whole idea here, though, is that once you hit a certain point, static friction will stop responding to it. It increases up to that point, and then once it hits that point, if you go anywhere past it, you switch to kinetic friction, and then you have to start caring about that in your equation. And that is not going to increase to match something. Kinetic friction is going to be based on the normal force and the coefficient of kinetic friction. It's not up to a certain number. It is that number. And then friction always works in parallel. I think it's LLEL. I'm bad at spelling parallel. I always get that autocorrected to the surface. So if it's and opposite the force applied. So if it's a slope, for example, it's going to either act this direction or this direction, up or down the slope. It just depends on which the force. If you're pushing this direction, it'll go the opposite parallel. If you were pushing down, it would go the opposite parallel and it would be going up. Same thing if it's on flat ground. It's either going to act to the left or to the right. It just depends. If you're pushing it to the right, friction acts to the left. If you're pushing it to the left, friction acts to the right. Now, the last types of forces that we have to interact with is tension. And tension is going to bring up an example. It's going to have me come back up here and use this little gap I have up here for normal force. So tension is what comes from ropes. And if you have a rope that's connected to, let's say I've got it connected to a ceiling, and I've got a ball connected onto my rope. Make sure that's in view. This ball is subjected to gravity, and then it's being supported by a tension force that's going upwards. But that tension force has to come from something. And if we go back to Newton's second law, or third law, every action has an equal and opposite reaction. Every force has to come from something. So our tension force that's coming upwards from this way is actually coming from this ceiling. This ceiling right here is going to also be feeling gravity because it's just existing on the planet. But usually, if it's not the thing we care about in the problem, we don't actually need to affect that. But that tension is actually coming from the ceiling. So this tension is going to come from the opposite side of the rope. So in our example problem that we had, thought I just accidentally kicked off the power to my computer and freaked out for a second. Apologize for the sneeze. So in our example of our bucket right here that we had, where we had a bucket attached to a string, attached to another bucket, and then that string is connected to something. Well, we'll call it connected to a pulley here. This bucket here is being supported by tension. From this bucket's perspective, that tension is pulling it up, but that upwards force has to come from somewhere, and that is actually pulling downwards on this bucket up here. The same thing up on this one. This bucket's being pulled down by a certain amount while it's being supported by tension from up here, and that means that this rope must be responding to it to support it by pulling back from whatever it's attached to. If it was attached to a ceiling, it would be the ceiling feeling that force. If it's someone holding it, if I draw a really crappy stick person up here because these are giant buckets, that person is going to feel that tension, and in this case it's going to be directed downwards. They're going to be having to pull down on this rope to be able to keep the thing in place to support it. So notice that basically I'm just taking the arrow, and in this case, this tension for this bucket is being supported upwards. So that means I need an arrow pointing downwards on it. And if I continue with it pointing downwards as it goes around the pulley, it's actually going to be pointing upwards. So it's going to be trying to pull upwards. The tension is going to be pulling upwards, so you'll have to pull down to cancel out that tension and to hold it. That's why if you were to have this on here and it's not supported, the rope would just go upwards, because that's the force, way the force is going. You'd have to pull downwards on it to prevent it from moving upwards. That's the direction it would want to go. Now, this gets back to the normal force up here, and actually I have space down here. So if you have an object that's sitting somewhere with another object on top of it, this first box is going to be experiencing, I'm going to do two smaller ones for my diagrams. So this first box is feeling gravity and is feeling supported by the normal force. But that normal force is actually coming from my purple box. And then my purple box is getting pushed down. And you could label it as Fn. It's equal to the normal force because it has to come from somewhere else. But it's really just the weight or the push of this top box. So Fw would probably be a more accurate thing, but I think it's easier to remember that, oh, it's the normal force from right here. It has to come from somewhere. So it comes from this lower box. And then this box is going to also have gravity, and it's going to have its own normal force. But this normal force here has my little purple star because it's this one that came from up there. Now, the question you might then have is, well, why don't we ever count where that normal force comes from here? Well, on a box resting on the ground, if I've got Fn and Fg, the location or the source of the normal force this time is the Earth. So if we were to zoom all the way out to this planet, and I'm going to make it a box that's still unreasonably large, but this box is being supported by the normal force and is experiencing gravity. Well, this planet, the whole Earth, is actually going to be experiencing a very, very slight gravitational pull towards the box, and is going to be experiencing the same normal force, or again, it's going to be experiencing the weight of the box pushing down upon it. However, as you may or may not have realized, the Earth is very, very big, and so it does not respond to it. Again, it's the same way that when you take something that's really, really light, like if I take this little piece of plastic here, I don't feel this piece of plastic interacting with my hand with the forces because I have such a massive more amount of mass than it. And since this box is so much smaller than the Earth, it responds to it with so much less of an acceleration that even though it exists, we don't actually even really perceive it. The Earth does not seem to react to any of the stuff that's sitting upon it. So again, the whole point that you should do when you're looking at a situation is first, this is again me trying to come up with this as best I can. Let's do 3 steps and hope I need that much space. Determine any motion. Now to do that, you may need to check forces versus the force of static friction. So compare to what the maximum static friction is. You've got to overcome that before you can move it horizontally. Or force of gravity. You've got to overcome gravity if you want to lift something vertically. So your first step will be, is there anything in the problem that indicates it's moving or that it could be moving? If it's something that's like sitting still, obviously there's not. And if there's no motion, then sum of your forces is equal to 0. If there is motion, you will have to figure that out with sum of the forces is equal to the mass times acceleration. If it's moving vertically, we'll just say vertical forces, you will have Fg, Fn supporting that force of gravity if it's stationary, and then whatever other pushes or pulls that you may have. And then horizontally, if it's still or if it's stationary, there should be no forces in the F direction, and that means that it will therefore equal 0. But if it is being pushed, pulled, or moving, then you're going to have friction involved, and you'll just need to determine whether or not you care about static friction or kinetic friction from that. So I know this was a little bit rambly. Again, this is just something that from the emails that I was getting, it seemed like this could be a little bit helpful to you. I really hope it helps. If there's any other questions you have or any other clarification that I can make, please let me know. Otherwise, this is Mr. Diamond signing off. Hope you have a good rest of your day, everybody.